In his 2016 IEC presentation, when Elon Musk first unveiled an early concept of Starship to the public, then called the Interplanetary Transport System, he outlined 4 ways in which SpaceX could reduce the cost of getting to Mars. The 4 factors include refilling in orbit, making the vehicle fully reusable, producing propellant on Mars, and choosing the right propellant. For the scope of this video, we'll cover the last 2 factors, producing propellant on Mars and choosing the right propellant. It's important to know though that all of the 4 factors involve the overall design of Starship and thus tie into each other. The importance of having gas stations in space and on other planets. In a previous video on Starship, we explained the importance of refilling in orbit and having gas stations or fuel depots on Mars. If you had to take all the fuel required for a full mission to Mars from Earth, you'd end up with a really big rocket, a huge rocket. The rocket would be so big in fact that you'd need large volumes of propellant to get it off the ground far less into orbit. The large amounts of propellant would increase the mass of your rocket, which would increase the amount of propellant needed, which would increase the mass of your rocket. Again, you get the point. Producing propellant on Mars makes it easy to have a sustainable gas station on the red planet. But in order to produce propellant on Mars, you have to actually be able to produce propellant on Mars. This means that you have to mine, collect, process, and store Martian material. This is called ISRU, or In-Situ Resource Utilization, and it doesn't only have to apply to Mars. There are a number of propellants that can be produced on Mars. SpaceX so far has mentioned at least 3 of these: kerosene in O2, hydrogen in O2, and methane in O2, more specifically deep cryomethalox. But perhaps the most feasible of the fuels is methane, which can be produced by the Sabatier process. This is just one of the reasons why SpaceX has chosen methane for its Raptor engines. The Sabatier process combines carbon dioxide and hydrogen in the presence of a transition metal catalyst like nickel or ruthenium at high temperatures to form methane and water. The Sabatier process is widely used on Earth and is even used on the International Space Station to convert CO2 from respiration into drinkable water. Where exactly is SpaceX going to get carbon dioxide and hydrogen on Mars? Mining CO2 on Mars. CO2 is probably the easy part. Mars is rich in CO2. The gas accounts for about 95.32% of the Martian atmosphere. Mining CO2 is as simple as extracting it from the air. When collecting CO2 from the atmosphere though, you're also collecting nitrogen, argon, oxygen, carbon monoxide, water vapor, and trace amounts of other gases. Perhaps the larger question that arises with gas capture of CO2 has to do with the purity of carbon dioxide needed for the reaction. Purity of CO2 potentially affects aspects like feed rate, conversion rate, and purity of methane produced. NASA researchers have done extensive studies on CO2 collection and storage so far and have primarily focused on 3 methods of CO2 capture, although more methods exist. The 3 methods are freezing the gas at cryogenic temperatures, mechanical compression, and absorption pumping. Even within these 3 methods, researchers have sort of isolated the first 2 as they're much cheaper and require less mass than absorption pumping. So which one will NASA or SpaceX use, freezing or mechanical compression? There are trade-offs between the 2 methods. For example, freezing at cryogenic temperatures has been found to purify the Martian atmosphere, yielding pure CO2. In some cases, freezing requires less power than mechanical compression. On the flip side, recent studies have highlighted some advantages of mechanical compression. Mechanical compression, unlike freezing, doesn't purify the gas. It collects the Mars atmosphere and feeds it directly to the Sabatier reactor. The advantage with using the Mars atmosphere mix of gases though is that in some cases it has been found to yield slightly higher CO2 conversion rates. Studies are still ongoing, and for now, researchers are still closely comparing both collection methods and are continually working on various prototypes of Sabatier reactors. NASA's Marco Polo, for example, is an ISRU processing unit that captures the Martian atmosphere and then freezes and stores CO2 gas, then feeding it to a Sabatier reactor where it's combined with hydrogen. Okay, so we've managed to collect the CO2, but where do we get the hydrogen? Mining water on Mars. The next step is mining water on Mars. To obtain hydrogen as a reactant in the Sabatier process, you first need to collect water. Water can then be split into its constituents, hydrogen and oxygen, via water electrolysis. That just means passing an electric current through water. The oxygen produced via water electrolysis is used as an oxidizer. Finding water on Mars. There are many locations on Mars where water exists in one form or the other. However, not all of this water will be available in the short term given technological limitations. Just as an example, there are large amounts of water ice located both and near the North and South poles. These ice caps, glaciers, and sheets are incredibly wide and extend miles below the surface of the planet. The North Polar ice cap alone is estimated to harbor a total volume of 821,000 cubic kilometers of water ice. The North Polar ice cap is about 100 kilometers wide and up to 2 kilometers deep, while scientists estimate that the South Polar ice cap, if melted, may be enough to cover the entire planetary surface to a depth of 11 meters. Researchers even speculate that there may be large volumes of liquid water or lakes located below these ice caps. In 2018, scientists at the Italian Space Agency detected a subglacial lake 1.5 kilometers below the southern polar ice cap. The lake extends 20 kilometers horizontally. So Mars has a lot of water, but while the water is there, as mentioned previously, accessing it is a whole other story. Accessing water at the poles would require serious advancements in excavation and drilling technology, and may be more of a long-term goal. Ground ice. For now, the most accessible water is available in the form of shallow ground ice. Data compiled from the findings from 2001 Mars Odyssey, Mars Express, and the Phoenix lander mission, and confirmed by MRO, have indicated that there is large amounts of ground ice located at latitudes between 55 to 58 degrees. In 2018, researchers using MRO found 8 sites where thick deposits of ice beneath Mars' surface are exposed in phases of eroding slopes. According to NASA, the deposits are exposed in cross-sections as relatively pure water ice, capped by layers 1 to 2 yards or meters thick of ice-cemented rock and dust. As I mentioned previously, the water doesn't only have to be present on Mars, we have to be able to access it. Even accessing water at these shallow depths require new technological and robotic advancements. In order to address the challenges, NASA is currently working on and supporting the development of various excavation robots and mining technology. One such robot that NASA currently has in development is RASSOR. RASSOR is designed to be as lightweight as possible while optimizing for the level of sturdiness, ruggedness, and agility needed in an excavation robot. The robot is designed to collect the Martian regolith and deliver it to an ISRU processing unit like Marco Polo, where the ice deposits and volatiles can be converted into liquid water. NASA has partnered with universities in the form of student competitions to further advance mining, drilling, and excavation technologies. NASA's Lunabotics, formerly NASA's Robotic Mining Challenge, for example, is a student competition where university teams must work to design and build a robot that can excavate Martian or lunar regolith and deposit it into a collector bin within 10 minutes. NASA's Moon to Mars Ice and Prospecting Challenge, similarly, is a student competition in which teams must work to design a drill that can extract water and assess subsurface density profiles from simulated Martian subsurface ice. As you can probably tell by now, in terms of making propellant on Mars, the chemistry is pretty straightforward. The Sabatier reaction combined with water electrolysis can produce the ideal fuel to oxidizer ratio needed for a return vehicle to Earth, such as Starship, while producing excess oxygen that can be used in life support systems. It also continually produces water. The devil, however, lies in the details. The challenges are largely very difficult engineering problems, actually making and powering a Sabatier reactor that meets all the mission requirements. Extensive research is still going on in terms of developing an ideal Sabatier reactor that can produce the purity and quantity of methane required for a return trip to Earth given time and power constraints. There have been a few experimental reactors developed so far, and they've been found to produce anywhere between 1 kilogram of propellant per day to around 0.3 kilograms of methane per hour. The 0.34 kilogram per hour number is the ideal production rate for a Mars Ascent vehicle as outlined in NASA's 2009 Mars Descent Reference Architecture, if you use 2 reactors. But as you can probably tell, this number is nowhere near to what SpaceX will need for Starship. On a full tank, Starship is estimated to need 240 tons of methane. By contrast, a Martian MAV requires 7 metric tons of methane. Quite a difference. One thing is clear, in order to make rocket fuel on Mars, at least for Starship, we'll definitely need higher performing Sabatier reactors. SpaceX has already stated that it would bring a Sabatier reactor either on its first or an early mission to Mars. It'd be interesting to see if the company will develop their own reactors or work with a third party. SpaceX is known for developing a lot of their hardware internally. so I won't rule out the possibility that the company might design their own reactor. SpaceX will certainly be leveraging on expertise and technology developed at Tesla in terms of energy capture and powering the reactor. Musk currently estimates that 50 to 60% of the electricity generated by solar panels on Mars will go towards propellant production. So while making rocket fuel on Mars isn't easy and there are a lot of technical steps, it's totally possible. It just requires reasoning from first principles and dedicated efforts to solve hard problems. Luckily, researchers have been working on this task for quite a long time. For now, it seems like Mars may be getting closer into view.